Welcome to Spring LIB.
This exercise, we're going to be talking about circular motion and friction force. So let's briefly review these two concepts. First, in order to study circular motion, we need to know that the centripetal acceleration, that is the acceleration pointing to the center of the circle of rotation of an object that's undergoing a circular motion, is equal to v squared divided by r, where v is the speed of the object and r is the radius. We also need to know that the friction force can be separated into two types of friction force. First, the static friction force that ranges from 0 to a value of mu s times the normal. Mu s is the static coefficient, the static friction coefficient, and n is the normal force that the surface exerts on the object. This is the static friction. Okay, and it increases, and the object will be still until the static friction force reaches a value of mu s times n. After the friction force reaches this maximum, and if there is another force acting on the object that will make the object move, another type of friction force comes into place, the kinetic friction, which is equal to the kinetic friction coefficient, mu k, times the normal. And with this information, we can proceed to the exercise. So in the exercise, we have an assembly line that is trying to transport cartons that have a mass m that is equal to 5 kilograms. And the assembly line is shaped in the form of a part of a circle. So basically, the cartons, they move in a circular path. We also have the information that the static friction coefficient between the cartons and the assembly line is 0.7, while the kinetic friction coefficient is 0.5. Also, we want the speed v of the cartons along the assembly line to be equal to 8 meters per second. And with that, we want to find what is the radius rho of the trajectory of the carton, that is the radius of the assembly line. If we don't want the cartons to slip, we don't want them to slide along the assembly line. So what we need to do, first of all, is to draw a force diagram on the cartons. So this is a carton. The forces that act on it are the gravitational force acting downwards. We also have the normal acting upwards. And since the carton is not moving in the y direction, we know that n is equal to mg, okay? So that the normal balances the gravitational force. And we also have the frictional force between the carton and the assembly line. Now, since the carton must not be moving relative to the assembly line, because we want the carton not to slip, then the friction force we're talking about must be the static friction force. Now remember, we are looking for the smallest possible radius of curvature that the assembly line can have so that the carton doesn't slip. Notice that the only force on the carton is the friction. The only force on the vertical plane is the friction force. So we have that the friction force is equal to the mass of the object times the acceleration, which we know it is v squared over r. Okay, now we are looking for the smallest possible radius. This means we should be looking for the greatest possible static friction force. Now, the greatest possible static friction force is mu s times the normal force. And the normal force, as we saw, is the mass times the gravitational acceleration. So this means that R, Vm's cancel out, so we have that R is equal to V squared divided by mu s g. So R is equal to V, which is 8 meters per second. Then we have to divide it by mu s. Mu s is 0.7 times 9.8 meters per second squared. So R, the radius, is 1.87. I'm sorry, this is 9.32 meters. Okay, and this is the radius of the assembly line, which concludes our exercise.